So I've got two applications of these separable differential equations that I want to talk about here. The first one is based on the idea of how fast a population grows. All right, so suppose the rate of change of a population is directly proportional to the size of the population. In other words, the bigger the population gets, the faster it grows. Right? I want to find a function that describes the size of the population with respect to time. Okay, well first, directly proportional. I mean, we know what that means, right? The rate of change, that's dy dx, and is directly proportional, so that's equals some constant times the population. Well, the population is y. So I want to solve this. Right? I want to solve this differential equation, and we know how to do this now. I'm going to separate it. I'm going to make this dy over y equals k times dx. Then I'm going to integrate both sides. The left side is the natural log of y equals k times x plus a constant. Okay, so now I'm going to solve this. I really do want to solve this for y. I want a function y equals. So let's raise e to both of these expressions. E to the log of y equals e to the kx plus c. E to the log of y is just y. And this, I'm going to split this up. I'm going to make this e to the c times e to the kx. E is a constant, c is a constant. Right? So e to the c is also a constant, and my equation is y equals a e to the kx. Right? And there's my equation. Right? Hopefully that's familiar to you, right? That is our standard exponential growth equation. You saw probably back in probably a college algebra class. All right. Now, how about that initial population? The initial population is y0. How does that fit into here? Okay. Well, look. Let's put this in here. The initial population is the population when the time is equal to 0 at the starting point. Well, I'm using x here, right? So let's actually change this up just a little bit. Let's make this y equals a e to the kt, right? To emphasize that that is a time variable. Okay. Then, when t is equal to 0, y is equal to y0. So let's put those in here. y0 equals a e to the k0 power. Well, k times 0 is 0, and e to the 0 is 1. So y sub 0 equals a, or really a better way to say it, a, that constant, is equal to the initial population. That means my equation is y equals y0 e to the kt. Again, hopefully that's familiar, right? That's your standard exponential growth or exponential decay equation. Okay, so here's something a little newer, right? Something maybe you haven't seen before. Newton's law of cooling. Right, Newton's law of cooling says the rate of change of the temperature of a heated object. We've heated something up. I always use kind of metallurgy as an example, right? You're working on some new metal refining process. You've taken this piece of metal, you've heated it up to some super high temperature, and then you take it out of the furnace and it's cooling down, right? It's cooling down. And what Newton's law says is how fast this object cools depends on the difference between the object's temperature and the ambient temperature. That is the temperature of the air, or if you've dropped it into some liquid to make it cool even faster, right? It would be the temperature of the liquid. Okay, so let's get some variables going here then. Let's let T be time, just like T usually is. I'm going to let H equal the current temperature of the object. Please don't ask me why it's H. I have absolutely no idea. It's a physics thing. That's the letter the physics guys use. And I'm going to let H sub A be the ambient temperature. That's a constant, right? We're assuming it's a constant. That's actually a slightly sketchy assumption, because when you take this super hot object and you drop it into this liquid, the liquid is going to start to heat up, right? But we're going to assume that this stays constant. You've got some kind of circulating system, for example, that is constantly moving the heated liquid away and replacing it with liquid at this constant temperature. Okay, so what does Newton's law say? Newton's law says the rate of change of the temperature, that's dH dt, is directly proportional, so that equals K times H minus HA. And the way this is usually written, the physics guys, they usually write this minus K. Okay, minus K. And the minus is kind of representative of the idea that it's cooling down, right? The rate of change is negative because the temperature is decreasing. Okay, so here's what I'm going to do. Just this is one of those little math things just to make my life easier. I'm going to let y equal h minus HA. All right, this is going to make things a little simpler for me as I go along. All right, so if this is the case, then dy dt equals dH dt minus dHA dt. Okay, but remember, h sub a, that's a constant. And the derivative of a constant is 0, which means dy dt is actually equal to dH dt. Okay, excellent. So put that in here. That means dy dt is equal to negative K times H minus HA. But H minus HA is just Y. And hopefully that looks super familiar. We did this already. That's exactly the differential equation we solved on the last slide. Only K is negative, but I don't care, right? That's not going to change anything. The solution to this is y equals y0 e to the minus k t, right? Just like it was on the last slide. Okay, now I'm going to go back, right? Because I don't actually want y's, right? I want the h's and ha's and so forth. So I'm going to say h minus HA, that's y, is equal to, let's see, y0. That is, let's call it H0 minus HA e to the minus KT. So that H0, see, I know I threw another variable on you here. H0 is, remember what it was on the last slide, it was the initial population. Our variable isn't population here, it's temperature. So it's going to be the same thing. H sub 0 is the initial temperature. In other words, it's the temperature of the stuff when you take it out of the furnace, right? It's that initial temperature, right? And really, a lot of textbooks, they'll stop here, right, and leave it at this. If you really want to get move that HA over and make this H equals H0 minus HA e to the minus KT plus HA. Okay, now let's do a little reality check here. All right, let's say we take the limit of both sides of this as t approaches infinity. equals limit t approaches infinity of h0 minus ha e to the minus kt. And I'm gonna split this up. Plus the limit, just applying the limit rule here, t approaches infinity of ha. So in other words, what I'm asking is, after a really long period of time, what's the temperature of this thing? I want you to think about that. I know I've kind of started the process, but I want you to kind of think about that for a second and see in your head what you think it should be. All right, because like here's what's going to happen. The limit. Well, let's take it one step further. Let's bring this h0 minus ha out. Limit t approaches infinity, e to the minus kt. Plus, what's this limit? The limit of a constant is a constant. That's just ha. And what's this limit here? The limit is t approaches infinity of e to the negative kt. Well, that's 0. Right, that's 0. And 0 times h0 minus ha is 0. So my answer is just ha. And if you think about it, that's exactly how it should be. Eventually, the thing is going to completely cool off, and its temperature is going to become the same as the ambient temperature. So that's exactly the kind of thing we would expect to happen.